This is part 2 on graphs having to do with Hamiltonian and Eulerian circuits. We just looked at some different types of paths and trails, but Eulerian means every edge is met once and only once. If you end up back at the beginning, it's called an Eulerian circuit, or we just call it Eulerian. And then if you end up somewhere else and it's not a circuit, it's called an Eulerian trail. Okay? The bridges problem, think of each of these as land. Like this is the land mass at the vertices, the island or the shore. And what are these? What would these represent? Those are the bridges. So this is the land, and this is the bridge. And what's cool about this is that whole complicated story with that whole geography can be changed mathematically into this setup. And what's unique about it is, does this look at all like what we saw? I don't think it does, but it has the same properties. So whatever you could do on the bridge drawing, you could do on this. So the question is this going to be Eulerian, semi-Eulerian, or neither? So if we started here and we went here, oh, that's not going to work. So we want to get rid of that. Okay, let's see. Let's start here. Go there. Ooh, that almost worked. Did anybody get it to work? How about this? Nope, then that one's high and dry. So this one, would you say Eulerian, semi-Eulerian, or neither? I think that one's probably a neither. Now let's look at the degrees. Here we have 1, 2, 3, 4, 5, 3, 3, 3. Okay? Here's the deal. If you have any vertices that are odd, it's not going to be Eulerian. If you had all of them were even, is that Eulerian? Boom, 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 boom. Yeah. What if you had, trying to see how we could do this with 4 here, and then did that. Is this going to be Eulerian? Yeah. Did I do that twice, though? Yeah, I started here, so I'm fine. So I went here, here, yes. And I did it, okay? So the idea is that if you had all of these, 1, 2, 3, 4, 4, 4, 4, 4, you got it made. It's going to be Eulerian. All of them are even, no problem. What happens the moment you stick an odd one in there? Can't be Eulerian, but it could be semi-Eulerian. Is that all right? So this is theorem 1. And it's any of the vertices of odd degree, it's not Eulerian. Okay, you can see some proofs, but you'll probably get the gist of it. A graph is connected if and only if there's a path between any pairs. Now that's kind of obvious. Is that connected? Is this one connected? Could, it says, if and only if there's a path between each pair. So there's these have a pair, these have a pair. Well, those have a pair. Do these have a pair? No. But as soon as you do that, now it's connected. Now this one doesn't pair with these, but it pairs here, pairs here, pairs here, and so on. So there's where and I think that one's a little obvious. Simple graph is bipartite if and only if each circuit in the graph is of an even length. So let's say we have the 2 by 3, our favorite. And it says it's bipartite, it's complete. So you would have this, this, and purple. That. Is that complete bipartite? So let's look at the circuit. Is the circuit even? 1, 2, 3, 4, 5, 6. Is that even? Yep, so there you go. So that's kind of an interesting theorem. This is your theorem 2.
So, what if there's just two vertices on the edge? Is that bipartite?
I think we talked about this already. I think on either one k of 1 comma 1 is not bipartite. I don't think so. And you can use this definition to prove it because it's not even. Yeah. Simple graph is bipartite. And then the last one here is the most important one. Actually, I think this is the last one. This is the one I want you to know. Would you put a star next to this? If you learned one thing today, this is the one I want you to know about. And that is a simple connected graph with n vertices and e edges has to satisfy the number of edges. Let's say we have 4 points. What's the least number of edges to connect all those points? 3, right? 4 points, 3. What if I added 5? 4. And 6. So does n minus 1 make it make sense to you? So the least you could do is n minus 1. What's the most it could be for edges? Not infinite. Handshake thing. 1, 2, 3, 4, 5, 6. And then you have pairs. This look familiar? And I think I got them all. I'm not saying I did, but I think I did. So we showed that with n choose 2 was the shortcut. N factorial over 2 factorial over n minus 2 factorial. So it's going to be n times n minus 1 times n minus 2 factorial over 2 times n minus 2 factorial. Do you see where n times n minus 1 over 2 comes from? That's for the complete graph of those. That's the most. So this is the least, and this is the most. So your edges are somewhere between there. Turn to your neighbor and explain that one right now. All right, then the last one, and they showed that in the proof kind of like I did. Any simple graph with n vertices and more than this many edges is connected. And so I'm going to let you think about this one. 1/2 n minus 1, n minus 2. It's going to be a simple graph with n vertices. It's going to have this many more. So the edges are going to have to be greater than this one. What do you notice about this and the previous one for the maximum? What happened to n and n minus 1? They decreased by 1. So since they decreased by 1, is that n minus 1 maybe, comma 2? N minus 1 times n minus 2 factorial over 2 times n minus 3 factorial. So then you can see these canceling out, and then you'll get that. So what they're doing there is they're saying that any simple graph with n vertices will have more than that many to connect. And you can play around with some of the problems and see how that works. Here's some really interesting little puzzles that you can try. Okay. And then for homework, let's just do a couple of these. Number 1, is this going to be Eulerian? Means it can go through all the edges and end back at the beginning.
Yep.
I see a thumbs up. Look at the degrees. 2, 2, 2, 2. What are these? 4. So that's definitely Eulerian. How about this one? Why do you say semi? I mean, they even show you that it's ending up at a different place, but look at the degrees. All of these are 2 except for the last 2. These are 1s, and so that won't work. So this would be semi. You're going to be able to access all the vertices with one and only one edge, but you're not going to end up at the beginning. And what if I put one more edge here? Now would it be Eulerian? Yeah, notice that these turn to 2 and everything's even again. Make sense? Okay, how about this one? See. 2, 2, 2, 2, 1, 2, 3, 4, 5, 5, 5, 5. Do you have it? The only chance, oh yeah, and then there's 4 in the middle. The only chance is it to be non-Eulerian, and then how many odd ones are there? 4, so that's too many. So this is going to be neither. Remember, you can have 2 odd degrees and be semi, but as soon as you have 1, it's neither, and as soon as you have 2, it could be semi. And then I'll let you try these and answer 2, 3, 4, and 5. 7 and 8 are really cool problems that kind of apply to your. Those are the answers to the bridge problem. So I'll give you about 3 minutes. Go ahead and get started on those. Just a quick reminder, Eulerian means that it's all the vertices are connected by an edge and they end up at the beginning. What's semi? All edges end up somewhere else. That's it.